Hello, everyone. My name is Micah Thorpe. I'm an undergraduate researcher at the University of Maryland, Baltimore County, and I had the pleasure this summer to conduct research under the direction of Dr. Yetming Chiang and under supervisor Cole Fincher. And my project was lithium dendrite behavior in ceramic solid-state electrolytes. Okay, so the advancement of lithium-ion batteries has fueled the progression of electric vehicles and will continue to be vital for the future advancements in technology. Before I get started into that aspect, I want to first talk about how a battery functions so we can have an understanding of that. So seeing the poster in this image here with the charge and discharge of the battery, lithium ions during charging flow from the cathode through the electrolyte into the anode, and on discharge, they flow from the anode back to the cathode and vice versa. And that's just the correct how rechargeable batteries work. And most commonly used in the field of batteries are liquid electrolytes. And these liquid electrolytes have organic compounds that are flammable, and those organic compounds break down and form acids when a battery fails, and when the battery is heated up due to dendrite formation. Well, this project provides a quantitative process to predict the growth speed and behavior of lithium dendrites in LOZO based on voltage, current, and the behavior of the crack seen visually. Establishing an understanding of lithium dendrites growth in LOZO provides a baseline for testing filament growth and other solid electrolyte materials, as well as other electrode materials. So as I alluded to before, lithium dendrites short the battery. And when they grow directly across and short the battery, it heats up the battery and causes the battery to fail for liquid electrolytes. For solid electrolytes, the dendrites will crack the electrolyte and go across and reach the other side and short the battery very similarly. So that's why this study is important, to understand how the cracks form and why they form and under what conditions they form and under what conditions they split. Based on previous work and studies into the fracture behavior of tempered glass, you can assume that with more current applied, there's faster deposition of lithium ions on the dendrite tip, which means greater stress buildup at the surface. And if we assume that the ceramic electrolyte behaves similar to tempered glass, the greater stress that you apply to the glass, or in this case, the ceramic, the more cracks will form. So in order to visualize this in our entire process, we use a very thin 30 micron thick polished LOZO sample of solid electrolyte. And use a thin sample so that the dendrites grow linearly and not down and just across the battery. Lithium electrodes are pressed on and heated up on a hot plate to melt the lithium onto the LOZO. The system is assembled inside of argon glove box. And then the lithium electrodes are connected to probes and then to the potentiostat, where we can apply constant current to the system, alternating constant current to the system. Let's see as the first video clip. The first dendrite branching occurs when a constant current is applied. And this is not necessarily what we expected. What we expected is what we see in figure 3, where when we increase our current, there's a branching in the dendrite. And then we drop back down to 4 microamps from 16 microamps. And then our fifth image, we jump to 8 microamps and we get a split as seen here. And that was the last of the splits for this set of cycles. They do continue in the next section for figures 9 to 13. But we did not see a crack split when we applied 8 microamps in figure 8. On figure 9, we jumped from 8 microamps to 16 microamps, and we see a 3 split in the bottom, and at the top of the image, we see a 2 split that's further visualized in figure 10 when we drop the current to 8 microamps. In figure 11, after we stopped flowing 8 microamps and then started again at 8 microamps, we saw a 2 split pictured here. And when we stopped to increase our current to 32 microamps, our largest jump. In the bottom right corner, you see a split of at least 5 lithium dendrites that form when we jump to 32 microamps. And then we see a 2 split at the top. It should further be seen in figure 13 as dendrites grow at a lower current. So from these results, we see that crack splits tend to occur when the current set point is increased, as well as starting and stopping at the same current rate. And these results support a hypothesis that with the greater current, there'll be greater stress and greater flow of lithium ions into the dendrite tips, and therefore greater crack splits and faster growth of the dendrites. So moving forward with this work, our next steps are to improve our methods and need a better microscope to better image the solid state electrolyte and hopefully come to a conclusion on the surface for greater understanding into whether or not the lithium dendrites are filling the entire cracks of the solid state electrolyte, or is there a vacancy at the tip, just for further understanding. And in addition to those advances in our methods, our next big question is whether or not the application of external pressure, as seen in this figure in the conclusions, with like clamping and applying pressure externally to a thin, like rectangular electrolyte sample. And if we do the same experiment with external force, will that affect the propagation of the lithium dendrites? Our hypothesis is that it will, since the ceramic electrolyte behaves mechanically, and the greater external stress is applied, the greater stress required to propagate cracks. So hopefully that's a result we'll see, because then this will provide a solution to this dendrite formation and a possible way to limit its effects of failing a battery. And I want to take this time to acknowledge the people who have helped me with this presentation, who made this research possible. Those people are Michael Wang, Will Wakefield, Maria, Cervantes Gonzalez, Carlos Barajas, Toby, Pedro, and Francesca Vaccaro for helping this poster. Thank you.